All right, let's begin. Welcome back to CS3510, L16A. I was going to cover, B. I was going to cover more randomized algorithms, and I had something prepared. And then this morning I woke up and I wanted to do something else. So we're going to cover something else, which is adjacent to randomized algorithms, zero-knowledge proofs. In some sense, each of these is just a protocol. A protocol is just an algorithm among a set of players. A zero-knowledge proof is a demonstration of knowledge. In the sense you have two players, you have a prover and a verifier. Something like this. They can exchange messages between each other, but eventually the prover tries to convince the verifier of something, the truth of some statement, you know. And a proof is exactly what you think like in a mathematical context, where person A, a proof is very non-interactive in the mathematical sense, where person A says something, they say something, they say something, they say something, and then the reader is convinced of it. Zero-knowledge proof differs from this really in two ways. First off, that the proof could be interactive, in the sense that the prover can say things, the verifier can ask questions, the prover can say things again, the verifier can ask questions. At the end of the day, it is the prover's job to try to convince the verifier of the truth of something. So the prover has to then output a convince that they are convinced by something. So first off, it's different than a mathematical proof because it's interactive. They can be an exchanging of examples or whatever. And second off, the verifier only need to be convinced like 99% of the time. The prover can incorrectly convince the verifier with some small error, but most of the time they should be correct. Now, zero-knowledge proof is exactly what it sounds like. It's zero knowledge. We'll talk about a more formal definition of knowledge. But essentially, you can convince someone that you know something, you know an answer to a problem, without actually revealing what the actual answer is. So you can convince someone that you know something without telling them what it is. That's what a zero-knowledge proof is. So we'll go through some classic examples today. First classic example is where's Waldo? Does everyone know where's Waldo is? Does anyone not know where Waldo is? Okay, good. Where's Waldo is just for anyone who's too shy. Where's Waldo is you have this picture, okay? And then there's 1,000 little people drawn over the picture. But the point of the Where's Waldo game is that you're looking for a location on the page where Waldo is. Okay? Now, technically, in an algorithm sense, what is the time of Where's Waldo? Yeah, it's linear, scan the page, okay? So in some sense, that's not a hard problem necessarily to solve. But it's difficult in a practical sense if the page is big. I claim that you can convince someone you know where Waldo is without actually telling them where it is. So if you have two people, one can convince the other they know where Waldo is. Here's the non-zero knowledge way to do it. You point at Waldo, you say there's Waldo. So you've told them where Waldo is. They're convinced that you know where Waldo is because you told them. But unfortunately, you told them. You can actually convince someone where Waldo is without actually revealing to them where Waldo is. What you do is you take a piece of newspaper that is 4 times the area or twice the length. You cut a hole of the newspaper directly in the center. Let's see. It's going to be like. Okay. You cut a hole in the newspaper directly in the center, and then you place the Where's Waldo book underneath the paper. Now, they do not see the X and Y relative position of the book relative to the newspaper. And because it's 4 times bigger, they have no idea relative to the newspaper where it is. But they can look through the newspaper and see Waldo in the middle, right? Now, you could reveal to them later where Waldo actually was if you could reveal what the relative coordinate position between these two. But this is an example of how you can convince someone you know something without actually revealing what it is. And this is usually like an introductory example. But this is how you can convince someone where Waldo is without actually revealing the position of Waldo. Questions on this? Are we convinced that if I were to do this to you, you would believe that I knew where Waldo is without actually knowing that you could find where Waldo is? Right? There's a more classic example that's for a slightly harder problem. And again, this is a children's example. Suppose there's a tunnel with something like this. There's tunnel A and then there's tunnel B. There exists a gate between the two tunnels with a lock and a key. Okay? you have Alice and Bob here who are playing around, right? Alice wants to convince Bob that she has the key. Okay? So what Bob says is, okay, Alice, go into the tunnel. She goes into a random choice of a tunnel. She goes, let's say, through tunnel B. Bob flips a coin and says, come out of tunnel A, or he says, come out of tunnel B with 50-50 odds. Okay? If she comes out of the tunnel that she just came through, Bob doesn't know that she has the key. But if she comes out of a different tunnel, then he's convinced she has the key, right? Now, there's a chance that Bob says come out of the tunnel that she already went in, and therefore learns nothing, right? So let's say Alice chooses to go through the side of B, and he says come out on B. From his 50-50 guess, he actually learns nothing here, right? But 50% of the time, he's going to ask her to come out of the opposite tunnel than she says, right? So the first time he plays this game, he's convinced only 50% of the chance that she's right, right? What happens if we play this game 10 times? Yeah. If we play this game 10 times and Alice actually knows the key, he can be convinced up to 1 minus 1 over 2 to the 10 times, 2 to the 10 probability, right? So the more times that he does this, the more iterations he says, Alice, go in this tunnel and come out of this tunnel, he can be convinced with certainty that Alice has the key, without Bob actually knowing what the key is. He actually doesn't know anything about the key. But you repeat this a certain number of times, you're going to be convinced that it is the key. Another classic example is blind taste testing. So let's say you have Coke and Pepsi. Can anyone tell the difference between Coke and Pepsi? Yeah, okay, everyone can tell the difference. Let's say I gave you could convince someone that you could tell the difference between Coke and Pepsi without explaining what the difference is. You give them 2 cups, one is Coke, one is Pepsi. You have them 50-50 identify which one's Coke and which one is Pepsi, right? They'll reveal to you which one is Coke and which one is Pepsi. But let's say if they know the answer, they're going to 100% of the time tell you the right answer. What if they don't know the answer? Yeah. Let's say they don't know what the actual answer is. They're going to make a complete 50-50 guess. Okay? They're right 50% of the time, though. So you do the trial again. Complete 50-50 guess. They're right 50% of the time. Complete 50-50 guess. They're right 50% of the time, right? So if someone is right, it can only be, if someone is wrong, it can only be sheer coincidence that they guessed correctly 20 times in a row, 50 times in a row. But if they're wrong, with overwhelming probability, they will make a mistake. If they're right, then you could be convinced that they did it right every single time, right? So in both of these examples, though, know that Bob is not convinced 100% of the time. Just an overwhelming probability that increases with the number of rounds played, right? That's kind of another example of zero knowledge. Let's do a more practical example. So let's suppose Alice and Bob both have 2 polynomials, right? Let's say f prime and f, okay? And let's say Bob is the prover, and he wants to be convinced that Alice has the same polynomial as Bob. Now what do I mean by the same polynomial? In the sense like this is maybe a multivariate polynomial like x squared plus 2xy plus y squared plus z to the 4th, whatever. It's some function of x, y, z in several variables, right? Alice and Bob Alice wants to convince Bob that she has the same polynomial, but she doesn't want to share what the polynomial actually is, right? So they want to exchange some messages in such a way that that Alice convinces Bob that Alice has the same polynomial. Now, what do we mean by the same polynomial is that if we were doing this a single variable case for all x, f prime of x is equal to f of x, right? We can be convinced those are the same if that's true. That's what we mean by equality of polynomials. So a bad thing is that Alice could just send the polynomial f over and Bob could just check it and then be like, yeah, that's fine. But we perhaps are in a situation where we don't want to send the entire polynomial. So we want Alice to convince Bob in such a way that doesn't reveal what the polynomial actually is, in case someone's eavesdropping, right? We just want to be convinced that it's the same polynomial. So what we can do actually is following something called the Schwartz-Zippel lemma. What? Schwartz-Zippel lemma? Also, this was named after two guys, technically, who were at Georgia Tech, DeMillo and Lipton. DeMillo and Lipton were two other theoretical computer scientists who figured this out like years before, like 2 years before Schwartz and Zippel, but no one remembers them, so they unfortunately give credit to Schwartz and Zippel. But so the Schwartz-Zippel lemma basically says that if R is drawn randomly from a domain S, and the probability that a polynomial R is equal to has a root is equal to the degree of the polynomial divided by the size of S. You could prove that, I'm not going to. But essentially, if you draw a random point from some specific domain, and the point, what is the probability that the point is a root of a polynomial? That's what it is saying. Essentially, this is very small, right? The probability you randomly guess, you have a polynomial, you know its points. The probability you randomly guess a point and it happens to be a root is very, very small. That's what the Schwartz-Zippel lemma says. But that kind of makes sense intuitively if you think about it, there's a lot of points and very few roots. The reason we care about this is that we could consider the case of f equaling f prime for some g of x to be the case that f prime of x is minus f of x, right? So if the difference of the polynomials is 0, then we can be convinced that those two polynomials are equal. So let's suppose, in a simple sense, the polynomials have very high degree. What is something that Alice and Bob could do so that Alice could convince Bob that they have the same polynomial? Send over roots. Are you familiar with Lagrange interpolation? If you send over too many roots, you have the whole polynomial. The polynomial is uniquely defined by its roots. That would actually work fine, though. Yeah. But which points? Yeah. Exactly. Oh yeah, you have that. You have the same polynomial. What's x0? Oh, I have f of x0.
Won't that describe the whole polynomial?
Ah, great question. And the answer is if you send over the number of points, which is 1 plus the degree, then yes. But let's make the degree really high.
Okay.
We cannot amplify this arbitrarily. There are ways around this, but I don't want to get too technical. But this can convince someone that you know what the polynomial is, right? So Bob is going to get a point and then be like, well, f of that same x naught is equal to my f prime of x. So at least our polynomials intersected those 2 points, okay? Then Bob is going to say, okay, what about x1? Alice is going to return f of x1. And then he's going to be convinced that these are the same. Right? If you think about it, what's the probability 2 random polynomials intersect at the same value? Very, very small, right? Take any two, just draw any 2 polynomials. Right? The probability, let's say they're quadratic, the probability they intersect twice is almost negligible. In fact, if 2 quadratics intersect 3 times, then they're in fact equal. But this is how Alice and Bob can play a game to convince one or the other that Alice knows that they have the same polynomial, right? And then they can swap places, and then Bob can convince Alice that they have the same polynomial, and so on, right? This is a primitive that can be amplified into other things, but for now we'll just kind of leave it like this. Questions on this? Is this convincing? Do you believe that Alice can convince Bob that she has the polynomial without revealing the polynomial? Again, notice that all that is revealed is a set of x, y points. And as long as those are less than the degree, then no person who's eavesdropping and listening in can ever actually learn what the polynomial is. Right? Okay. One of the first examples of a zero-knowledge proof was not actually called a zero-knowledge proof, but it was a method invented to play poker over a telephone. If you want to flip a coin over a telephone, let's say you call your friend Alice and you say, I call heads. And they say, oh, no, it was tails, sorry. How can you be convinced that she didn't just change the answer after you said heads, right? You can solve this with such an argument. Are we familiar with a hash function?
Yeah.
In what context?
Linked lists and collisions.
Yeah. So hash functions have two important-ish properties. Let's not get. We can spend a year on this science, but given y, finding x such that h of x is equal to y is hard. So inverting the hash function in some sense is hard. Finding a value that hashes to that specific thing is difficult. If h of x is equal to h of x prime, then x equals x prime with overwhelming probability. So a hash function can be used a lot of time as a checksum. You upload a file to a server, you compute the hash, check that it matches the local hash. You don't have to recheck the bits of the file. When you can compute the hash and just compare those. Because with overwhelming probability, two files have the same hash if and only if they're the same file. Yeah?
So this is kind of off topic. Does the whole hash thing depend on the fact that all data types created by people have like some commonalities that we can't really describe, but that must exist?
A hash function is explicitly uncompressive in the sense that every Blu-ray you've ever ripped compresses to the same size hash. So that is true specifically for lossless compression algorithms like zip and stuff. But hash functions are simply a little check. You can take a hash function outputs a fixed width object, say 128 bits. It takes as input anything. So in fact, by the pigeonhole principle, there must exist these collisions, two different files that map to the same output. Yet we think it's statistically impossible to find such a collision, but they must exist. So collisions exist, but they're improbable to find. This is a practical thing rather than
Right, because, well, if you were considering over the space of all possible like things that
Yeah.
you take the hash of,
yeah.
obviously you could find a lot of collisions.
Could you? There's a difference between collisions existing and you finding collisions.
Well, right, but if you have two things that hash to the same thing, the probability that they would be the same would still be low. If these could be any...
Non-constructively, yes, but algorithmically, no. And that's kind of an interesting dichotomy here. Hash functions, we know that everything collides all the time, like overwhelmingly so, but we can't find a single collision. For any strong hash function, we've never found a collision, ever. One of the hash functions is used in Bitcoin, and it's just constantly being beat to death. It's hashed over 1 billion times. We've never found a duplicate. Through all that mining power that people are throwing at it, no one has ever found a collision. In fact, it's known that these kinds of functions exist. They're called one-way functions. Exist if and only if p does not equal np. So in fact, you only get all those nice statistical properties if some other things are true. But we don't know if those other things are true. Either way, we have functions that appear to have this property. So under certain assumptions, we can derive certain protocols. Here's how you can, Alice and Bob can play a game convincingly to ensure that you can flip a coin over a telephone, okay? Let's say Alice wants to flip the coin and Bob wants to call it. Alice is going to first flip the coin. Let the coin flip be 0 or 1, okay? Then Alice is then going to generate randomness, something really big, okay? He's then going to do what's called a commitment scheme. He's going to send to Alice, here's the commitment. It's going to be the hash of the committed bit with this randomness r, okay? He has the randomness, okay? Bob is going to make a guess, C prime. Alice is then going to reveal what the guess actually is, okay? And Bob is going to be happy if C equals C prime. This is called a bit commitment scheme. So first off, does the protocol work and can it be cheated? Let's answer those two questions separately. Does the protocol work? Alice commits to, it's called a commitment. They send this commitment over. Bob does not send the answer until he receives the commitment. He's like, I'm not going to make a guess until you send me this commitment. But the commitment asserts, in some sense, that Alice can't change the answer. She sends over a hash of C, R. He then makes a guess, and then she reveals the answer, right? Now, how does Bob verify the commitment? He plugs in, let's call this H, and he checks if the first commitment is equal to if I were to hash it myself. And this symbol, by the way, just means concatenation. So what he does is he just checks the thing that Alice sent me, and he says, does that equal what the commitment she made originally? If it does, then he knows that she did not change the answer, right? So she's good on that end. Is it possible for Alice, for this to still be correct, but for Alice to not change, for Alice to change the answer, but the hash to not be equal? Why not? I guess what I'm asking is, let's suppose the first bit was a 0. We are looking for some hash that hashes to the same value. Essentially, Alice has to look for some r prime such that that is true, right? Can they do that? Yeah. So basically, if Alice can cheat, that implies that H is not what we would say is collision resistant. So you take the contrapositive of that. If H is collision resistant, which we cannot prove, but we assume H is collision resistant, then Alice cannot cheat, right? The important part, of course, is that the commitment is sent before the guess is made. She's locked in, and she says, here's the answer, I'm locked in. Now, does this prevent adversarial behavior? For example, it could be the case Alice acts maliciously and says, I'm not going to play the game. He guessed correctly, I'm just going to give up. I'm not going to tell him anything. I can refuse this step. Let's not consider those kinds of cases. We assume that Alice is honest, but this commitment protocol allows Bob to detect if Alice actually is honest, right? He doesn't necessarily have to trust Alice any more than she's going to correctly send the messages. He only has to trust the security of the hash function more than anything, right? This is called a commitment scheme. Questions on this? In some sense, every password login system is a kind of zero-knowledge proof, where the website owner never actually stores the passwords, right? They store hashes of the passwords in a complex way, hashes of hashes and so on. So when you type your password in, you're never actually sending your password over the internet. You're sending a hash of your password over the internet in some other complicated way, and then it compares the hashes server-side. That's how they know who you are identity-wise. In some sense, that's a zero-knowledge proof where you convince the server that you know a special string without revealing what that string actually is, right? Okay, this is called the commitment scheme. Are there any questions on the commitment scheme? Okay, let's do one more thing. What is the definition of knowledge? When is something considered knowledge or not? This is kind of an open-ended, maybe even philosophical question. What is knowledge? How can you convince someone of knowledge? Two questions. Is knowledge information?
Yes.
Okay, that's as best as I can hope for. Is all information knowledge?
Yes.
Why? I'm not convinced of that.
Well, are we thinking philosophically or mathematically?
Both.
Philosophically, if it's information but you're perceiving it, then you know it, so it's knowledge.
What if it's a random string?
Well, you still have knowledge of what it is.
I suppose. I guess that. I can't argue with that, but that doesn't fit into the framework that I'm about to present it in. Okay. The formal definition of knowledge is that it is a solution to a problem that is difficult. For example, the square root of 125 is not knowledge. Okay? In some sense, it has to be something that it is difficult for the verifier to know. The prover wants to convince the verifier it actually knows knowledge, but we need a definition of knowledge. It couldn't be knowledge. It couldn't be something that the prover could just compute themselves. So the way we formalize this is that knowledge is a witness to an NP-complete problem. right? If the verifier, for example, is polynomial time bounded, they cannot compute a satisfying assignment to SAT if P does not equal NP, right? But the prover would like to convince the verifier, oh, I know a satisfying assignment. That would be a definition of knowledge, right? It has to be something the verifier could not perhaps compute themselves. We would not consider that knowledge. So in some sense, this is not maybe a very practical definition, but it is an interesting one because a witness to a solution is something that is difficult to compute for both parties. So it is, in some sense, information that is gained when the verifier learns it, right? One of the main results in the theory of zero knowledge proofs is that all of NP has a zero knowledge proof. In the sense that for every NP complete problem, the prover can convince the verifier that they actually know the solution, the witness for whatever that problem happens to be, right? So you can convince someone you know a satisfying assignment to a CNF or something without actually revealing the satisfying assignment. This is historically important because back in the day there was like zero knowledge proofs for every little individual problem. They were like, here's how you could prove a number is prime. Here's how you can prove this is, you know, I don't know, whatever. There was all little individual cases. And then somebody comes along and just does the whole thing, right? And in fact, if you think about up to completeness, we only need a zero knowledge proof for a single NP complete problem. If we have a zero knowledge proof for a single NP complete problem up to polynomial time reduction, then a satisfying assignment to one, the satisfying assignment is the same thing as a subset sum, right? And those all map to the same answer. So all we need is a zero knowledge proof for one NP complete problem, and we're good. The NP complete problem we'll choose, surprisingly, is 3 coloring.
Not Mario?
Not Mario. We will give a zero knowledge proof for 3 coloring, right? So we have the prover and the verifier here. And the prover has a coloring. They know the coloring of some graph. Again, this coloring is perhaps they knew a CNF or something. They knew some satisfying assignment to a CNF. They performed the reduction from SAT to 3 coloring, and the satisfying assignment corresponds literally to the coloring of the graph, and so on, right? So they want to prove to the verifier V that they know what the 3 coloring actually is. The prover wants to convince the verifier, I know what a 3 coloring of this graph is. They both already know what the graph is. The prover wants to convince the verifier it found a 3 coloring. But it doesn't want to reveal the 3 coloring. It has to do so in zero knowledge, right? Questions on the problem before we define the protocol. How can you effectively convince someone that you've colored a graph without revealing the graph, revealing the coloring in some sense? Yeah, I mean, honestly, that's going to work. So what you do first is let the graph be V1 to Vn, and let the colors be C1 to Cn. So the coloring is as such, right? What the prover first does is permute the colorings, right? If, in some sense, if Bob were to reveal the colors over and over, then that could somehow reveal the coloring after enough rounds of that, right? So we don't want to do that. So the first thing the prover is going to do is commit, for all I, commit color CI, right? What do we mean by commit? This exact commitment scheme. Use this exact thing as a sub-protocol. We're going to commit, we're going to send a hash over, generate n random strings, n hashes, send those all over. Say, hey, here's the commitments for each of the C color, for each of the n colors, okay? Now, V is going to choose randomly some edge E is equal to VI, VJ, okay? The verifier is going to ask the prover about this. The prover is going to reveal it's going to open the commitments for specifically and only those 2 edges, okay? It's going to reveal Ri and Rj, which are the randomness for Ci, Cj, right? If it sends the hash over for those. So now the prover, the verifier knows a permutation of the coloring for just these 2 edges. So if the coloring Ci does not equal Cj, what do we know must be true? Yeah, these are different colors in the coloring. So in the coloring of the graph, the prover reveals to the verifier a single edge. It uses this commitment scheme to say, hey, I'll let you look at the coloring of one edge. What is the coloring? And the verifier can say, I picked this edge. And then the coloring is revealed to the verifier, and because they're different, it increases the confidence that it works, right? There's a few small problems here immediately, but we see that this can convince the verifier that the coloring is actually a 3 coloring. If overwhelmingly it chooses edges and none of them share the same color, for example, if Ci equals Cj, that's good, but if the colorings are different, they're not different, that's bad, right? Repeatedly open colorings, and then it's going to be convinced that it's fine. There's a small problem with this, very small problem.
It's imperfect.
What do you mean?
Like, with small probability, your prover could have a bogus coloring and you would still get all the right answers.
I didn't formally give the definitions here of something called soundness and other things, but that's okay. As long as the probability is small, the verifier, we consider this to be secure.
Would there be any perfect zero-knowledge proof?
No. In fact, it is known that you cannot have perfect zero knowledge for NP.
Okay.
That's a complicated result. Yeah.
So you're sending over, at the beginning, you're sending over a hash of all of the different, like, the pairs, right?
Correct. You send over things like H of, let's call it C1, R1, like that.
So you could just send over hashes where both of the colors are different, and when they ask for a specific 2 edges, like 2 things, then you just you don't know that the hashes sent over originally form. I don't know how to explain it properly.
You could use a coloring with 5 colors.
That is a problem. We'll get to it in a second.
Like I could just count how many they see.
So notice that it's important that the only thing that is revealed here are the commitments are only open for 2 specific vertices, right? So all the other commitments are not needed. It is true, though, that the prover does commit to all vertices, but it only opens 2 of the commitments, right, for that specific edge. So it is not the case necessarily that the verifier even learns the 2 colors, but it does learn that the 2 colors are different. One of the reasons that it prevents against this, there's another problem here, but one of the reasons this prevents against this is that the prover randomizes and permutes the colorings before sending them over, right? So it doesn't actually know what the true coloring is. It could be the case it asks about the same edge over and over and gets a different coloring. It just knows that they're differently colored. But if it's a valid 3 coloring, it knows it anyway, right? Could you rephrase your question? I think you're almost at a point that I would like to make.
I don't think I could rephrase my question.
All right. Are there any other? Important is the fact that the verifier must commit to the coloring of the graph beforehand.
What's the purpose of creating that coloring?
Because if it repeatedly, let's say Alice says, open this edge, 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 the verifier just learns the coloring. But we want it to be zero knowledge. We don't want to reveal the actual coloring. So we want the I keep saying Alice. We want the verifier to learn that the edges are colored differently.
Yeah.
But we don't want them to learn what the actual colors are.
So, what does the permute the coloring mean?
Permute the coloring means red goes to blue, blue goes to red,
You do that after
green.
committing to the
No, that goes before the commitment, before anything is sent.
Well, once you've committed, you can't mess with it anymore.
Exactly, correct. So it commits to the permutation of the coloring.
So you only send over one commitment, and they ask you multiple questions about edges.
No, every time you ask, that's another good point. This is the next point I want to make.
Multiple commitments. You send one for each.
Every time you open a new edge, the whole protocol is repeated. So this is exactly for one edge. You do this a second time, and a second time, and so on, right? You would do this every single time you wanted to reveal an edge. The whole commitment game would have to be redone. The prover would have to re-permute the colors, re-send over the end commitments, and then after that, the verifier would choose an edge to reveal.
Could you still get a clue as to what the coloring is because there are only 6 permutations?
You would learn from the permutations that every time you opened an edge, you would only learn that they are differently colored. But that's valid for any coloring.
No, I mean a bystander looking at that, who's seeing all the solutions getting passed down. Even though they're not all from the same coloring because they're permuted, there's only 6 permutations. So enough questions could give you a clue as to what's going on.
I don't think so.
Okay.
It's true that there are only 6 permutations, but the only person who knows the permutations is going to be the prover.
Yeah.
The verifier, convince yourself the verifier could not extract the literal coloring given single edges of each possible permutations.
Well,
And even if they could, there is a fix for that as well. But
okay.
sorry, go ahead. What was it?
Well, if you can extract the coloring, if we were doing this repeatedly with only 1, then in theory you could do it with 6. All you'd have to do is,
So,
every time you see the same vertex twice, you kind of fix it.
The verifier would not actually know what the coloring. So the first thing is that we assume that the verifier is honest, and that they don't try to deviate from the protocol. We just don't want it to be accidentally revealed what the coloring is. So the first thing is that we assume the verifier behaves honestly, and that's true in general in cryptography.
Yeah.
The prover could perhaps try to behave maliciously, but the verifier is always honest. The second thing is that also shouldn't matter because it would learn the colorings of different permutations. It wouldn't know which colorings belong to which permutation. It would be impossible for it to sort that.
Okay.
Yeah. So there's a zero knowledge proof for all of NP because 3 coloring is NP complete. You could reduce SAT to 3 coloring and then do the same thing for a satisfying assignment, and so on, right? In some sense, a protocol is just a randomized algorithm, but it's interactive in the sense there's multiple people, each doing multiple programs, sending and receiving messages to each other. And this kind of stuff only came after we really understood a little bit better about how randomized algorithms work. For example, we know that the prover must accept, in all situations of zero knowledge, the prover must accept with probability that's overwhelming but never perfect, right? There's always a negligible chance that the prover is able to cheat the verifier. But that's okay, because 99.99999% of the time might as well be 100. So in practice, this stuff works out really well. Right. Questions? Yeah.
What kinds of problems have perfect zero knowledge proofs? Like, where's Waldo?
Anything in P, I guess.
Okay.
Things that are the definition of knowledge, I do not think have perfect zero knowledge.
Could every problem in P have a perfect zero knowledge proof?
Yeah, here's an example. The verifier is assumed to be polynomial time bounded, so it just recomputes the solution.
Oh.
So not really, I guess that's not really zero knowledge, I guess, but there's other notions of statistical zero knowledge and things like this, like if you want perfect security, and maybe you don't want to assume existence of P versus NP, you don't want hash functions. You could spend your life studying these problems. The motivation here is, though, that this is all and only enabled by randomness. Convince yourself that we did not have certain complexity assumptions, and we did not have any randomizations, properties of randomness, as it works for computation. We don't have any of this. So, questions? All right.